hopefully I define barely too many things. I'll start. A polytope is the convex hull of finitely many points in Rn. And a face F of a polytope P is a subset where some linear inequality that's satisfied everywhere is an equality. So I can say there exists a vector in Rn and some value such that this is the linear inequality is satisfied everywhere in P, and F equals to where it's equal. So, and the face lattice of a polytope, just say P, is all faces ordered by containment. So if I have, say, a triangle, right, and I look at what are all the faces. So I see, like, here's some linear inequality, and then it's an equality at B. Say that, well, that gives you an idea of the faces. I also have an empty set as a face. If I pick this as my linear inequality, everything inside of this region. So I have the whole triangle as one face. Each of the edges there's these three edges, and then each vertex. And so what the picture I'm drawing here is, this is the Hess diagram of the face lattice, which has you draw usually a dot or something to indicate each element of the post set, and you draw an edge between them if one is contained in the other but there's nothing in between them. So this is the Hess diagram of the face lattice of a triangle. Right, all of the faces ordered by containment. And the interval post set or interval lattice, if it's a lattice, of some post set or lattice this is, I'll call it P. This is all intervals ordered by containment. Right? The intervals are just like so and if you look in general, the interval lattice, the thing you can notice here is this kind of looks like a cube, right? And in general, the interval lattice of any simplex will always be the face lattice of a hypercube. If I start with a D simplex, right? This is the face lattice of a D plus 1 cube. So you look at this picture, it kind of looks like a three-dimensional cube. So does that make sense? More or less?
Well, you're talking about the interval lattice of a
poset.
Of a poset, right. So
a simplex is a poset.
A simplex is not, interval lattice of, sorry, right, of the face lattice. Of a D simplex. So you start with a simplex, construct the face lattice, and then take the interval lattice of that.
You haven't taken the interval lattice yet, I guess.
All right, so I could give you an example of the interval lattice here, right? So an example of an interval is, let's say, this interval, right? One interval would be, let's make this as a set A, B, C, and I think I put the lower bound on the, let's put the lower bound here. Oh, it doesn't. Let's say B and A, B, C. Okay, this is a set consisting of A, B, C, and A, B, and I'll just write B, C, and B. So that would be this region here, right? This square is one interval.
Are these all faces of the cube?
These are all, yes. Take every interval in this, and you get a face of the cube. So if you take, for example, let's say your lower bound is B, and your upper bound is the empty set, you get again the empty set. That's a face also. If you take the empty set as your lower bound, and A, B, C as the upper bound, you get the whole cube. Right? And then all these edges appear as faces one step apart from each other in the poset. So in general, if you start with any polytope and you draw this poset, the face lattice, which this is what we would define to be the combinatorics of a polytope. This will usually look like it is a polytope. So the question is, can the interval lattice of the face lattice of any polytope be realized as the face lattice of some other polytope. So,
which would mean I could take the points of this pose set and put them into some Rn, and the inequalities would be...
That's right, yeah.
It's the same thing, right?
These inequalities would be...
I mean, I could take the convex
the
of this
intervals.
thing and I would get...
Yes. A polytope that has these edges. You start with your original polytope, you get a vertex for each face. You arrange them so that you take the convex hull, you get a new polytope, and the faces of this new polytope appear one for every interval in the face lattice of your original polytope. This is what we're looking for. Is this the case or not?
You want to restrict the dimensions to other polytope, or you don't care about the dimension?
So as it turns out, if you can do this, the dimension of the other polytope will always be d plus 1. It always goes up by one dimension, if you can do it. But it turns out that you cannot always do it. This is what I found.
Is it hard to see why it goes up by one dimension?
So I will explain that in a moment. I'll give you kind of a little bit of a picture of what's going on. So I want to say so some polytopes here, P1 and P2, these are combinatorially equivalent. If they have the same face lattice. These are, and they are dual if maybe this is not hard to see. The face lattice of one is dual to that of the other. That means you reverse the direction in the pose set. That's the dual of pose sets. So if you take this whole pose set, you start with some pose set, and you flip it upside down, right? Some other polytope that has that as its pose set is the dual. So for example, if you look at like a cube, right, the dual of a cube, maybe this is something you are familiar with from geometry a long time ago, or if you look at it now, this would be the octahedron, which would look something like this, right? This has a facet for every vertex, and arranged in the opposite, with the opposite orientation. So the talk I mentioned was about antiprisms. So in antiprism, the antiprism was not originally defined this way. This is, but it turns out this works as the definition. Is the dual of its interval polytope of, say, the interval polytope of P. I didn't say interval polytope. So if this is realizable, if the answer to the question is yes, then I call this the interval polytope. So, and there's, if you look on, like, for example, Wikipedia, they have lots of pictures in 3 dimensions of an so this would be a picture of an antiprism of a square, right? What it looks like is you get you take a copy of the original polytope and you take a copy of its dual, right? So one, you can think of a prism has like two bases. One is the original polytope. Both of them are the original polytope, and you have all these prisms all around the side of the larger prism, right? So but this one has 2 faces. One is, this is how we usually denote the dual. One is the dual of the other. And when you take this when you flip the face lattice upside down, right, you get a correspondence between faces of your original polytope and faces of the dual. And the other facets of the antiprism are the convex hull of pairs of corresponding dual faces of the 2 copies of the polytopes. This is, and that's actually how antiprism was originally defined, but now I look at it this way. Another way, if I flip this up so you can kind of see, let's say, looking down on it, I can draw it like this. Right, here's another picture. So
what is the interval? So you're saying that thing is unique? That
if this exists, it is, call it the interval polytope.
That's unique.
So it's unique up to the combinatorics. I mean, all of them that exist will be combinatorially equivalent.
The interval polytope is not the original polytope, but the polytope that gives you the
So
realization of this one.
it's an interval so combinatorial equivalence means just that you have the same face lattice. And this process tells you what that face lattice is. So trivially, every realization will have to have the same face lattice. I mean, because that's the defining feature of this thing.
But,
right.
So interval polytope is the one that whose face lattice is equal to the interval lattice of the face lattice of P.
That's right. Yes. So like in this example with the triangle, you start with a triangle, form its face lattice, look at all intervals. Each interval should be a face of the...
So the antiprism P is not defined for every P?
That's right. Not every P has an antiprism.
But this construction you said seems like you could make it geometric. You take a d-dimensional polytope in RD.
Yes.
Every polytope has a dual. You could
That's right.
pick, increase the dimension by 1. Right?
So you can do this process, and the requirement for the result of that process to be an antiprism is that, and this was the original definition given for an antiprism. When you look at this thing, you can see they're equivalent. Every face has a corresponding dual face, right? So two facets of this polytope that would be created by taking the original one, making a dual copy, lifting it up, take the convex hull of that, right? Two faces you'll have are the original polytope and the copy of the dual that you found, right? Those will have to be two faces, right? I mean, you can think analogously to making a prism. You have some kind of thing here, right? You take a copy of it upstairs, right? You get, this is quite not the best
When you
picture.
make a copy, you get corresponding.
Right. So this is like this. Yeah. So here you get corresponding faces. The requirement is right, and here you would say like every face of the original one and the copy, those two give you a facet of the prism. In the antiprism, you take every face of the original polytope, every corresponding dual face of the dual copy. That has to give you a facet, and those are the only facets you get.
So in general, this geometric construction might not work.
It might not work, and here's exactly when it will work. And this was proved, all right, some time ago. A polytope is perfectly centered when the orthogonal projection into the affine span of each face lands in the relative interior of that face. Okay, so here I'll give you some pictures of this, right? Let's say I draw this square, right, and the origin is in the very center. If I do orthogonal projection to each face, right, the affine span, I get, it lands in that face. So this one is perfectly centered, right? Also, the origin has to be in the polytope. Wait a minute. This should be, sorry. There's the trivial case, right? Each non-empty face. Of course, you can't really project into the empty set. So where this would not work is, let's say I have this other quadrilateral, right?
Orthogonal projection of what?
The orthogonal projection
Of the polytope.
Sorry, I jumped ahead. Of the origin. Into the affine span. Yeah, so sorry. Yeah, start at the origin, project orthogonally into each face. It should be in the relative interior. So if I start with the origin here, right, and I look at this one, right, the affine span is like this line here. If I project orthogonally, I don't make it.
this isn't even an affine invariant property, right?
No, this is not an affine invariant property.
Okay.
Right. And also you can note, like any translation of this will not be satisfied for, so.
Do you want the origin to be in your polytope?
Yeah, the origin has to be because you also consider the affine projection of the origin into the polytope, which means it won't move at all. So yeah, the origin has to be in the polytope. If the polytope is full dimensional, I mean, yeah, basically. So here is the result. This is the necessary, no, sorry, this is sufficient conditions, not necessary. So if you can find a perfectly centered realization, then you can get the antiprism by exactly what you suggested.
By taking the geometric dual. Right?
By taking the geometric dual, which is sometimes called the polar. And then you can kind of see what's happening here, right? If you, well, so the dual of this thing you could find by looking at a point here and taking a cone over one copy and a cone over the other copy. If you think about the dual, like look at this object, okay? If you think about here, you have a triangle. If you have a triangle, and you take, let's say, a dual triangle, right? And then you have some point at the bottom, and you form the cone going up over the triangle. This is one. Maybe I'll make the other one yellow so as not to be too, so as to make it more clear what's going on. All right. Let's say, and you have this other cone here, say, and you intersect these cones, right? This will give you a cube balancing on a point, like this picture. Maybe you can kind of see what's happening, right? The other way you can see is you can see what happens if you put a small triangle in here and then grow it, right? This can, the intersection of these two will give you a slice of this as you go down, right? As this grows, right, then you get this hexagonal region. It grows some more, right? And then eventually it comes out. So, and this, intuitively, this tells you why there's these other, I gave these other necessary and sufficient conditions, okay, which are the following. if I have polytopes P1, P2, these are a balanced pair when the first is they have to be centered. This means 0 is in P1, the origin is in P1, and also the origin is in P2, right? They have to be dual to each other. So, let's say the face lattice of one is isomorphic to the dual of the face lattice of the other. And cones over the relative interior of a face of each intersect an array if and only if they are dual faces. So this will kind of tell you where the vertices come from. If you look at this picture, right here, this is an example of a balanced pair. If you pick any one of these yellow triangles and say the origin is here, right? If let's say this vertex is opposite this this edge, say those are a dual pair, then if I look at the cone, this is the cone over one, and the cone over this one would look like this region, right? And the intersection of these two regions then is array. But if I look at, like, say, this face and the yellow face, right, then I get this yellow region like this, and I get this white region like this. Their intersection, which is between here and here, this area will not be array. So this is what the conditions are saying. Just you have dual faces should intersect an array, and that's it, nothing else. And they should always intersect an array. And then I showed this is necessary in sufficient conditions, right? So this may not immediately seem to make the problem that much easier to solve.
What's part of
As one, well, so
One of
a balanced pair is two polytopes. So if you can realize this as one of the two polytopes, you can realize this as one of the two polytopes if and only if you can realize the interval lattice as a polytope. So this gives you necessary and sufficient conditions. But it doesn't tell you yet exactly if you can always do it or not. Initially I had thought that probably you always can do it, but that turned out to be wrong. So these kinds of problems of realizing something are made difficult by there's this theorem by Richter-Gebert, the universality theorem. Does this make sense? My conditions.
It makes sense, but is any direction easy to see? Or?
So
Well, the one direction you should kind of show, right?
yeah, that if they are, you form. So if you have a balanced pair, you just take a vertex above one of the pair and a vertex above the other pair, and look at the cones going over these two regions, right? Now look at the cone over this region. This will give you some geometric intuition, right? You have this thing here, right? Say this is above this point, right? Now you form a cone over some face of this. Let's say this face, right? Now project that down onto, let's say this is in a plane, right? This is in a plane here, and this is up above, right? If you project this cone down onto this plane, you get, I'll draw this in yellow, you get this region, right? This yellow region will be the projection of this face of the cone.
The back face.
Yeah, the back face. All right. So if you have a dual one here, right? And you say, now what's the projection of some other face of the cone corresponding the cones over this vertex, right? The projection of that will be a ray that goes through here. So that's how you can go back and forth between these two.
So do you have some example showing something that's not perfectly centered, but is part of a balanced pair?
No, I don't have an example of that.
Okay.
Well, I mean, okay. In some sense, there is an example, because this is one polytope and that one's
Okay,
two
no,
polytopes.
so
But
I
right,
meant-
you start with this one, form the polar. So if you start with this one, you form the polar. If this was perfectly centered, you'll always get a balanced pair.
Right.
Right, and that fits in with this theorem, right? Because this is sufficient conditions, and this is necessary and
Is there a
sufficient.
polytope that cannot be perfectly centered,
Yeah. Okay.
which could be made part of a balanced pair?
So the answer to that I don't know.
Uh-huh.
That I'm not sure about. Yeah. So one direction is simple. The other one, I don't know. And that would make these conditions simpler, if that were the case. So let's get back to this. So Richter-Gebert, I think 1996. Is that right? Universality. This is the universality theorem for polytopes. Says for any system of, say, multinomial equations and strict inequalities, there exists a four-polytope with a space of realizations let's say modulo affine transformation, that is homotopic to the solutions of this system. So how this works is basically, so you specify some equations, like let's say I want x squared plus y squared equals 1, right? And then this gives me a circle. For every point on this circle, right, it's homotopic, so then I might get some region, but I'll have some realizations that correspond to each point on this circle. And then I can very smoothly around this and have my have the realization change, right? As you move around in the realization space, the vertices of your polytope will move around in space. But you can have one that looks like a circle, or any kind of other horrible thing, right? So I say horrible because if this is a search space, right, this is not a nice search space. If you want to find something, this makes it difficult. So using similar, there's a similar kind of, but there's kind of an antidote to this difficulty, and that is I'll have to define something else, right? Right over here. I'll say a polytope is algebraic when it has algebraic coordinates. Right, and here I mean the algebraic completion of Q. So for any algebraic D polytope, I'll call this P, there exists a D plus 2, let's say not quite, a combinatorial type, actually. Of D plus 2 polytope. I'll call it Q, with a specified face so that in every realization of Q, F is projectively equivalent to P. Does this make sense, the meaning of this? I start, you can give me some polytope using this. I find some face lattice, and then anytime, also this is, well, this is also, and this is realizable. So actually I should say, actually there's something a little bit stronger you can say. If you start with any realization of F, you can complete it to a realization of Q if and only if it's projectively equivalent to P, which is also the same as saying that Q is realizable. Although, I mean, I guess there's some question of definition exactly, but it wouldn't be a combinatorial type of polytope. So, but why this is important? This has a corollary, which I will show you to explain how to use it. Let S be some statement about a collection of algebraic polytopes of the same combinatorial type. So such that for any face S is inherited by some projective copies. This may seem of that face for each polytope, for each of the polytopes in the collection. So if I have right, this means, so this, I have some, right, these all have to be the same type. I'll use a script character for type. the statement, right, this takes as arguments some, if you think of it as a function, you can think of it as a function to the bool variables, true and false, right? This is saying for all f that's the face of this, right? If it holds for some of these, that means that there exists some projective transformations such that these are the statement will hold for these faces, right? This is the kind of property that I want. And if I have this a statement that is like this.
So it should be pi I and that I. No?
Oh yes, right. Yeah, sorry. Yes. Then S holds for some realization of every combinatorial type if and only if S holds for some realization of every projective type. So this means that if we're interested in whether there is a polytope always having some property, this makes our life easier, right? As long as it has this kind of inheritance. So an example of such a property would be, does P have rational coordinates, right? So this would inherit to a face, because if you have a polytope with let's say it has all rational coordinates, you have something with all rational coordinates, you pick out, and then pick out a face, of course, then the face also has rational coordinates, right? So if it's true of the polytope, it's true of the face. This is the kind of statement, right? So this is saying that if we want to know, for every combinatorial type of polytope, can we realize it with rational coordinates? It's enough to answer the question, for every projective type of polytope, can we realize it with rational coordinates? And the second question seems much easier in some sense. Like, you might think maybe not. Like, maybe you can always realize it, right? You would think, so in 2 dimensions, let's say this is not rational coordinates, right? You could think, well, here's a nearby point. I'll just adjust my polytope a little bit. There you go. Now it has rational coordinates. But if you restrict yourselves to projective types, right, the answer you could see is clearly not, that's not the case, right? There's this cross ratio. If I take the cross ratio of, if you're familiar with the cross ratio of, let's say four rays passing through, or four lines intersecting a line, take the cross ratio of these 4 points, right? This will always be projectively invariant, right? So if this is not rational, then this pentagon cannot be realized by, this projective type of pentagon cannot be realized with rational coordinates. You can't perform any projective transformation that gives you all rational coordinates, right? So this corollary is telling you that from this property you can deduce that there's some polytope that in every combinatorial realization it does not have rational coordinates. So that gives you, maybe that's a simpler way to understand this theorem. So I can apply this to this property, right? It's not obvious that it's easier to find a balanced pair or not. But it turns out it's not as difficult to find a polytope that cannot be balanced with some copy of its dual using projective transformations. And that's exactly this. If I draw a square and I add in these kind of beveled edges, I get. So if I start with this, right, and I start with its polar, right, select maybe I don't know if I didn't explain the polar, but there's a canonical way to find a dual. If you find the canonical dual in that way, right, those two polygons, any projective transformation will not make them into a balanced pair. And that you can do by just like, you write down the coordinates, right, make the projective transformation, you can write it as a matrix, you have make the terms of that all variables, the terms defining the projective transformation all variables, right, if here's the dual will look something like this, right? You'll have this, well, you can see if the origin is here. If you look at the perfectly centeredness property, because that's easier to see, you have something coming out here. It just becomes solving a linear algebra problem, basically. Look at, make all the terms of the projective transformation variable, and if you write it all out, you'll see that there's no way to satisfy all of them simultaneously. So I think I'm running out of time, but...
So I don't understand what this example is showing.
That
That could be one of my questions.
Okay.
Okay.
Right. So I'm kind of skipping over the details a bit, but this...
You are now going to construct a...
So this, if you take this polygon here,
Yes.
and you take its polar,
Yeah.
the canonical dual of it,
Yes.
and you perform any projective transformation to this polytope and any projective transformation to the copy of its polar, the canonical dual, you will never get a balanced pair. It's impossible to get a balanced pair. There's no projective transformation. So that means that you cannot get, that means that there are pairs of polytopes that cannot be made into a balanced pair by projective transformations, which means that there's pairs of polytopes that cannot be made into balanced pairs by combinatorial equivalence, any realization with the same combinatorics, right? Which means there are polytopes with, I erased it now, such that the antiprism of this polytope is not realizable. That's the following the logic backwards. Are there other questions?
Is that David Richter then? David Richter?
Jürgen Richter.
Jürgen
It's one person. Jürgen Richter did it.
Jürgen Richter Gilbert, okay.
That's his last name.
So any other questions about this?
So do you know... Do you know what the polytope... So this one is going to give you something by... maybe this theorem,
Yeah, by this theorem.
Do you know what it looks like? I mean, you have the combinatorics of... Is it easy to go from the combinatorics of this one
So the thing
to
is...
build back up this by this Bevel's theorem?
Yeah, so actually I have my own proof of this.
Okay.
But using either way, the resulting polytope is tremendous. It just, the vertices go on and on.
I see. Okay.
So it'll be a really huge polytope. So that's an interesting question also. Is the
Huge meaning number of vertices.
huge number of vertices? but it'll be 4-dimensional. So because this goes from D to D plus 2, this is another thing that another part of the corollary. The gap, if there's a gap, there can be a gap of at most 2 dimensions. So then you'll have a 2-dimensional gap where you'll have to use some other argument. And if you start with any 3 polytope, then you can realize the antiprism. That's actually not that hard. There's one realization of a 3 polytope polyhedron, you could say, which is the mid-scribed realization, and that one will be perfectly centered. If you know,
Antiprism of any 3 polytope
is realizable, yeah. Every three polytope has an antiprism. And this gives you a complicated 4 polytope that does not have an antiprism.
I see.
Another question? Yeah, let's thank the speaker.